In this video, we will learn what is non-homogeneous recurrence relation and we will learn how to solve problems based on non-homogeneous recurrence relation. So now, definition, recurrence relation of the form an is equal to c1 an minus 1 plus c2 an minus 2 plus etc. plus cn an minus k plus f of n, where f of n is a function depending on n or a constant. Then we say it is a non-homogeneous recurrence relation. That means, you see there is a function, right? In homogeneous recurrence relation, we have a relation or an equation of the form and there is no f of n term in homogeneous recurrence relation. So when you come to non-homogeneous recurrence relation, you have a function, okay? We have a function f of n, that's what you have to notice. And that f of n, what about that f of n? That f of n is a function depending on n, okay? It's a function in n or a constant. Now in non-homogeneous recurrence relation, we have to find the particular solution also. Now how to find particular solution? So let us learn the method to find the particular solution. You see, we have the particular solutions when f of n is of this form. Here is a table. When f of n is of the form in the column, then we have to take the general form of the solution as given here. So when the form, first form a stands for constant. When f of n is a constant, then form of the solution an is the homogeneous solution, non-homogeneous solution, okay? An is the non-homogeneous solution and the solution is taken as c. And if the function f of n is n, that is a function, okay, which is n, then form of an is c0n plus c1. If the function f of n is n square, then the solution an is c0n square plus c1n plus c2. If it is n raised to t, then c0 n power t plus c1 n power t minus 1 plus etc. plus ct. Then a raised to n, comma, a is a simple root, then cn a raised to n is the solution. A raised to n, where a is a double root, then cn square a raised to n. A raised to n, a is a triple root, then cn cube a power n is the solution. A power n, a is not a root, c a power n is the solution. So you can note down this table, and here in this table we have how to form the solution a and how to take the general solution of the non-homogeneous recurrence relation. As you know, simple root means not repeated, the root occur only one time, and a is double root. What is double root? We know it occur twice, okay? If some values like 2, 2 or 3, 3, we say that root is a double root. Triple root, if it comes 3 times while finding the root, or while finding the root, if the root is repeated thrice, then we say that root is a triple root. If that may not, when you take a raised to n and a is not at all a root of the characteristic equation, then we say it is not a root. So you will understand more while doing the problem. Here is a question. Solve s of k plus 5, s of k minus 1 is equal to 9, comma, s of 0 is equal to 6. So we should identify whether it is a homogeneous recurrence relation or it is a non-homogeneous recurrence relation. And when you look into this 9, we have a constant. Just now we learned f of n will be there, and that f of n will be a function of n or it is a constant. Then we say it is a non-homogeneous recurrence relation. You see, when you come to non-homogeneous recurrence relation, in this recurrence relation you have the function f of n, where it is a function depending on n or it is a constant term. So in this question we have the constant n, okay? We have the constant terms, not n, constant term. From n we can, from 9 we can assume that f of n is a constant. You can take like this. Here f of n is a constant. So we say this is a non-homogeneous recurrence relation. So since you have 9 here, so we can rewrite the question. First we have to solve this problem as in the similar way we did for the homogeneous recurrence relation. That's what you learned first, right? So now let me rewrite it. Given recurrence relation can be written as an plus 5 n minus 1 is equal to 9, where a0 equal to 6. So we can rewrite it in terms of a. S can be replaced by a and k can be replaced by n. So an plus 5 an minus 1 is equal to 9. S of 0 means initial condition a0 is equal to 6. So you can take this k minus 1 to this suffix, okay, k minus 1. You can take n minus 1 instead of that, because we are learning in terms of an minus 1. So I have rewritten this one. Now characteristic equation, in order to write the characteristic equation, we need the order first. To find the order, highest term is an, lowest term is an minus 1. So we can subtract n minus 1, okay, we learned this earlier. We have to take n and we subtract the least term suffix, that is n minus 1, that is n minus n plus 1, expanding we get this. So order is 1, okay, order is 1. So we have to start with r raised to 1. So earlier we learned if order is 2, we have to start with r square. Order is 3, we have to start with r cube. Here it is order is 1, here the order is 1, so we start with r raised to n plus some constant term is equal to 0. So we take, what about the constant? Coefficient of an is 1, coefficient of an minus 1 is 5. So we have to take 1 and 5, and RHS we have to take 0 while writing the characteristic equation. Don't take 9, we have to take 0 while writing the characteristic equation. So 1 plus 5 is equal to 0. We take the coefficient, right? Earlier we learned this coefficient of an is 1, coefficient of an minus 1 is 5. So we take 1 and 5 and we equate it to 0. That is, since order is 1r plus 5 is equal to 0. So since order is 1, we have to start with r raised to 1. Coefficient is 1 and 5 is equal to 0. R plus 5 is equal to 0. R is equal to minus 5. So roots are real and distinct. So we can write the solution when r is minus 5. We call it as homogeneous solution, ANH. Since we have to find the non-homogeneous solution also, first characteristic equation and its solution is an power h, that is homogeneous solution is alpha 1 minus 5 raised to n. So we learned when the roots are real and distinct, we can write the solution as alpha 1 r 1 power n, right, alpha 2 r 2 power n plus etc. Here there is no r2, we have only r1. We have only r1. So no need to take these terms. We take only this one, that is alpha 1 minus 5 raised to n, because r1 is minus 5. So we get this solution alpha 1 minus 5 power n. So now let us find the particular solution. We call the non-homogeneous solution as particular solution. So while taking this, we know we have to take f of, here f of n is 9, right? So from the definition, you see you have the function f of n, and instead of f of n we have 9 in this question. So we have to take f of n as 9, that is the constant. So from the table, when it is a constant, you see when f of n is constant, you have to identify like this, okay? This a is nothing but 9. A is nothing but 9. So f of n is 9, that is constant. Form of an. What is form of an? An is assumed to be c, okay? An is equal to c. That's what how we are going. Okay, here f of n is equal to 9. Therefore, an particular solution, an power p is equal to c. From the table, we have to assume an as c. I have taken p to denote the particular solution. Now we have an given. We are taking the given recurrence relation. What is the given recurrence relation? An plus 5, an minus 1 is equal to 9, where a0 equal to 6. And here, taking that, what is an? An is c. Then what will be an minus 1? That is also c. Because there is no change when you constant will not change, right? There is no n term to replace. So if an is constant, then an minus 1 will be also a constant term. An is constant means an minus 1 is also constant. If an is equal to something n, what will be an minus 1? It will be n minus 1. Suppose an is equal to n square, what will be an minus 1? Replace n by n minus 1. N minus 1 the whole square. So n, if you take n minus 1, replace n by n minus 1. If an is n square, then replace n by n minus 1. You get n minus 1 the whole square. So here there is no n. Okay, so no need to no need to get confused. Just what we have to do is an is c, then an minus 1 is also c. So taking, now substitute it, an is c, 5, an minus 1 is also c, so 5c is equal to 9. Adding these two terms, we get 6c is 9, c is 9 by 6, 9 by 6 is 3 by 2. So now a and p is, so we can write, so we have to find c and we have to substitute it in the particular solution. What is the particular solution? Our assumption from the table, a and p is equal to c, right? Now what is c? C is 3 by 2, so a and p is 3 by 2. So a and particular, that is particular solution is 3 by 2. Now let us come to the general solution. General solution means we have to add a and h plus a and p. That is a and h we know, a and h already derived, alpha 1 minus 5 raised to n. So we add those two values, alpha 1 minus 5 raised to n plus this is a and p is 3 by 2. This is equation 1. Also now condition is given, a0 is 6. We have already learned this. N is 0. An is an. What about n here? General form an. Here we have a0. So instead of this n, you can take 0. Okay. So when n is 0, alpha 1 minus 5 power 0 plus 3 by 2. Here you get a0. Equation 1 implies a0 equal to alpha 1 minus 5 power 0 plus 3 by 2, which is equal to, what is a0? a0 is equal to 6. So we have to equate it to 6. Now alpha, any number power 0 is 1. So we get alpha 1 into 1. That is alpha 1 plus this minus 5 power 0 will become 1. Here you have 3 by 2 is equal to 6. Now alpha 1 is 6 minus 3 by 2. Well, taking LCM, 12 minus 3 by 2, that is 9 by 2. Alpha 1 is 9 by 2. So now substitute it in equation 1, which gives the solution. Equation 1, an is equal to alpha 1 minus 5 power n, right? Instead of alpha 1, we can take 9 by 2. So 9 by 2 minus 5 power n. 9 by 2 minus 5 power n plus 3 by 2 is the solution. So whenever initial condition is given, so what is the use of initial condition? To find the constant in the solution. Constant here is alpha 1. So using this initial condition, we got the constant substituted in the solution. So when a recurrence relation is non-homogeneous, all that you have to do is you have to find the homogeneous solution first. You have to find, so this is the homogeneous. You have to find the homogeneous solution first. Then you have to find the particular solution. Particular solution depends on the value of f of n. Here f of n is constant. So we can assume an as c. So an minus 1 is also c. Substitute it in the given equation to find c and substitute it in an. So after finding an, you can add. So usually general solution means you have to add both the solution. A homogeneous solution and particular solution, you add it. Then using the initial condition, find alpha 1 and substitute it in this equation. That gives the solution of the given non-homogeneous recurrence solution. So you can try this question on your own, okay? Solve the recurrence relation an minus 5 an minus 1 plus 6 an minus 2 is equal to 2. a0 is 1, a1 is minus 1. So here n minus 2, you will get the order as 2. So you have to start with r square. Okay, start with r square, you get the roots. Then fn is 2, so an is c. Substitute it, no change. C. From this you can find c. And what you can do after finding c, you get the particular solution. Okay, then you can add homogeneous and particular solution. Okay, so particular solution and so adding, you get equation 1. Adding homogeneous and particular, then when a0 is 1, n is equal to 0, you get the solution. When a1 is minus 1, that is n is 1, you get a equation. Okay, here also you get a equation. Okay, you get equation 2, you get equation 3. When n is 1, then solving, you get alpha 1 and alpha 2. Substitute it in the general solution to get the answer. Okay, this gives the solution.